use the Wronskian. After using the Wronskian, we get the value 1. We check if it is linearly dependent or independent. Since it is linearly independent, that means we are guaranteed that these solutions form a fundamental set of solutions. Number 8 is asking us to solve the following differential equations and find the general solution. So for this, if anything is in this form where it's y to some degree plus y to some degree plus or minus y to some degree, we can use y is equal to em of x. And what we're going to do is take the derivative of this multiple times and plug it into here. After we take all the derivatives, we get these values for our y's. So when we plug in our values into a, we get this emx in parentheses m squared plus 2m minus 3. We factor out the e to the x because all of our y's have an e to the x in front of them. So after we factor this, we can get m is equal to -3, 1. So that is our m values. So when we get our m values, we have to plug it into this. After we plug everything in, we get y is equal to c1e -3 of x plus c2e of x. And that is our general solution. It's general because we still have c's, constants, in our solution, so it is not particular. So for part B, after we get our y values, we can plug it in, and this is what it'll look like. After that, we can see that we only have one m, which means our y1 is equal to c1e -2x. Well, we need two m's, so from here, we need to use the reduction of order method. Using the reduction of order, this is the formula right here. After we plug everything in, we're going to get this. Our p-value is going to be whatever value is in front of y prime. If there's a value in front of the first y, we have to divide the entire equation by it, and that will be our p-value. Whatever this value is over whatever is in the front here. After we integrate the top part, we get this. We can bring the c1 down, so it'll be e to the -4x times c1. We can bring this c1 outside of the integral with this e -2x because it is a constant. After we bring out our c1, we're left with this. Our e to the -4x's cancel out, so we will just have a 1. And the integral of 1 is just x plus a constant, which is what we have right here. Splitting this into here, we get this part right here. We can see that this part is equivalent to this part, so our y2 is going to be this. From here, since these are equivalent, what we can do is just take this portion, what we have written here, and set it like this, and then just put a y in front of it. And that is our general equation. For part C, this is what our equation is going to look like after we plug in all of our y values. And there is no easy way to factor this part out. So what we're going to have to do is use the quadratic equation. So after we use the quadratic equation, we get this. And since we have a negative on the inside, we will have a I that we have to have out front. And then solving the square root, we're going to get I times 4. So we get that m is equal to 3 plus or minus 2i. So since we have a complex solution because of this I, we need to use Euler's identity. Euler's identity, we need to use that identity, and that is this. For both of our m's, whatever value is not with the complex part is our alpha. Here we have our beta. And the same thing for this one, we have alpha and beta. So after we plug everything in, also this is supposed to be an alpha, not an x. I made a mistake and wrote x instead of alpha. But after we plug everything in, this is going to be our final answer. That is our general equation. So for D, we will plug in all of our y's, and this is what we get. So we need to factor this portion, and we get m minus 1 squared and m plus 1 is equal to 0. For this m plus 1 part, we can get this y1. For the m minus 1 part, we need 2 y's. However, we only get 1. So after we find the y for this, which is this, y2 equals c2 e to the x, we have to use reduction of order to get the second y value. So this is the reduction of order that we are going to be using to solve this. After we plug everything in, we're going to be left with this down here. This portion right here, we can move out here and we can solve it like this. We can say we have e to the x times e c1, and e to the c1 is just going to be c1. Since this is a constant, we can move it out in front of the integral. So that's going to place it right here with e to the x. And then now that we have that, we are no longer going to have the c1, so we just have e to the 2x over e to the 2x. We're going to take these out, and we're just going to be left with 1 dx. The integral of 1 is just x plus some constant, which is where we get this from. And then if we factor this in, we get this. Now, to get our final solution, we have to combine this part, and this part. After we combine everything, we get this is our general equation or general solution. For number 9, we're asked to determine whether this is a general solution for this equation. So first thing that we're going to need to do is we're going to look at our y1 and our y2 and make sure both y's are valid in this equation. To do that, we're going to have to take the derivative of both of them twice and plug the respective values into this equation. If that equals 0, then we can use the Wronskian and see if it is equal to 0. If it does not equal 0, then this is the general solution to this equation. So our first y1 is this x right here. The derivative of that is 1, and the derivative of that is 0. So after plugging this in, we can see that this is going to be 0. So after we make that 0, we can see that y prime is just equal 1. So this can cancel out as just being 1. And we're going to have an x substitute in right here. Well, after we do that, this part and this part are identical, minus the negative sign here. And since there is a negative sign, these both will cancel out, meaning that we have 0 is equal to 0. So this is a solution. In our second step, so after we factor everything out, we have this is our y2, this is our y prime of 2, and this is our y double prime of 2. So after we plug all of our values in, we get this equation right here. And we just need to make sure that this equals 0. There's a few ways to do this, but we are going to do it the way where we factor everything into each other so we can fully see that it equals 0. So after we factor out most everything, we are going to get this equation. So from here, we're actually going to need to factor out again. We can actually combine these two things, and we are still going to need to factor this into here. So after we factor it out, it looks just like this, and all we have to do is distribute the negative sign right here into this. So once we do all that, we're left with this being positive, this being positive, and all of this in the middle being negative. So we can start canceling things out. So we can cancel these out. We can look at what we have next, and we can cancel this, negative 2x squared e to the x, out with this. We can cancel this x squared e to the x out with this x squared e to the x. And then we can see that these last two cancel out just like this. We are left with 0 is equal to 0. That means that this also is a solution to this equation. Now, for step 3, what we need to do is have our y1 and y2 values go into the Wronskian and ensure that it does not equal 0. So after we plug everything into our Wronskian, this is our y1 and our y2. So this is our y1 column and this is our y2 column. Now we have to multiply these two and subtract the product of these two. So from here we get this. Once we factor this x in, we can see that these cancel out and we're just going to be left with an x squared e to the x. So this does not have to not be 0 on the interval negative infinity to infinity, since we are not given an interval. It just has to not be 0 on some interval. And we can find our interval by setting this equal to 0. Remember, this cannot be 0. So e to the x cannot be 0, so we can just get rid of this, and we're just left with x squared is equal to 0. So x cannot equal 0. So what this means is our interval is going to be from negative infinity to 0 and 0 to infinity. Now we have to pick one of these intervals, it doesn't matter which, so we can just choose 0 to infinity. So we can write our answer like this. Since both y1 and y2 are solutions and do not equal 0 on the interval 0, infinity, y is a general solution to the equation. Number 11 is asking us to find a second solution, y2. We are given y1, and we have to use that to find a second solution for the given equation. To do this, we have to use the Wronskian, and all we're going to do is plug our y values into here, and we get our y2. So looking at A, this first value has to be 1, so we have to divide everything by t squared. So then after we do this, we can cancel out this t, and we're left with 1t on the bottom, so that means our p is negative 4 over t. So after we do this, these negatives become positive, and we can focus on this portion right here. And after we take the integral, we get 4, and then in parentheses ln of t plus c1. E to the c1 can be brought out front as just c1 over here, and then this 4 can go into our ln, so we're going to get t to the 4th. And after we do that, the e and the ln can cancel out, so all we're going to be left with is t to the 4th. After we do this, we rewrite it like this. These are the same, so it just equals 1. After we take the antiderivative of this, we get t plus c2. Then we need to factor this in, and what we're going to be left with as our y2 is c2 times t cubed. However, we actually do not need this c2. If we look back to the equation, we're only given this. We only need c2 when we're putting it in the general equation. Since it's only asking us for y2 and not the general equation, we can write this as just t cubed. For b, we have to divide everything by x, and our p value is whatever is in front of our y prime. So this means our p value is going to be equal to negative 1 over x. After plugging everything in, we can rewrite it like this. These negatives can turn into a positive. And looking at this portion, we are just going to get e ln of x. Since, as we stated last, we're not worrying about the general solution, only the y value, we don't need to worry about the c's. So from here, the e and the ln are going to cancel out, leaving us with just an x on top. From here, we need to do a u sub. We need to make our u this variable, so we can get rid of this. Replace our dx with a du and get rid of our x. After we do our u sub, we're left with this. What we need to do now is flip this sign squared of x to get it up here, and how we can do that is turn it into a cosecant squared of u. And the antiderivative of cosecant squared of u is negative cotangent x plus c. Since we are only looking for the y value, we aren't taking the c value, so we can get rid of that. This should actually be a u, and we can rewrite our cotangent as negative cosine over sine. From here, we can see that our sine of x cancels out. As stated earlier, in this step, we don't care about the constants. There should be a c here. There should also be a c after taking this integral inside here, but there isn't because we're not looking for the constants. So what this means is that this constant, this -1 constant, and this 2, so -1/2, goes away because it is absorbed into the constant. So we're left with our final answer being y2 is equal to cosine of x squared. For 12, we're asked to solve the following differential equations. So since we have a cosine of x over here, we need to use this form of yp. Yp is equal to a cosine of x plus b sine of x. We must take the derivative of that and the derivative of that, so we can plug it into here and here. After we plug everything in, this is what we're left with. Since we have sines, we can think of this equation as having a 0 sine of x. So what we're going to do is take our cosine values and set them equal to this value, and then take all of our sine values and set them equal to this value to find a and b. So after we separate everything, this is what we're left with. We can go ahead and get rid of the cosines and get rid of the sines. So we are just left with -5a plus b is equal to 2, and -5b minus a is equal to 0. Now we have to work with these to get our a and b values. So after we find our values, we're left with a equaling 5/13 and b equaling 1/13. So our final yp is equal to 5/13 times cosine of x plus 1/13 sine of x. This is important because we also need to find yh, which is the general solution. Once we find that, we can combine our yh and yp. To find yh, we need to use yh is equal to emx, and then take the derivative of that, take the derivative of that, and substitute these y values into this part of the equation. So once we plug everything in, this is what we get. We have to find this value, we have to find m, so that it does not equal 0. And to do that here, we can take the quadratic equation. Once we plug our m's into this equation, we get this value right here. So now for our total y equation, all we need to do is combine this and this. So after we combine everything, we're going to get our y value to be this. And that is the answer. For part A, we found yp first, but for part B, we're going to find y of h first. To do this, we're going to plug in these to our left side. So we need to find this part right here, we need to find m. So we can see that our m values are m plus 4 and m plus 0. Do this, you get m squared, you get m0 plus 4m plus 0, which equals this. So that means your yh is equal to c1 e negative 4 of x plus c2. So on the right side, we have to solve these separately. We have to solve for x squared, and then we're going to solve for x e to the negative 4x. For yp, we are going to use this right here for this x squared part. So normally in solving our yp, we would write it like this after we plug all of these values into here. However, we can notice that this is asking for an x squared, and we do not have an x squared in here. So what we have to do is actually go into here and make this x cubed. This is going to be x squared, and this is going to be x. So what that means is that this value is going to be 3ax squared plus 2bx plus c, and then this last y double prime value is going to be 6ax plus 2b. So now we're going to plug all of these back into here correctly this time. After we plug it in, we have to add these so we can look at our x values and our constant. Then we are just going to move everything into its respective equivalents. So we have this, which we're going to pair with this x squared, and then all of our values with an x with it, we are going to put with our 0x, and then our constants are going to go together with a 0. So in doing this, we can get rid of the x's. We see that on this side we're just going to have a 1 instead of an x. So that means a is equal to 1 over 12. And if we plug that into this part, we are just going to get 1/2 plus 8b. And what we can do is subtract both sides by 1/2 and then divide both sides by 8. So we're going to get that b is equal to negative 1/2 times 1 over 8. So we're going to get negative 1 over 16. And then if we plug that into here, we get 4c plus negative 1 over 8 is equal to 0. If we move the 8 over, so we add 1 over 8 to both sides, and then divide by 1 over 4, we'll get c is equal to 1 over 32. Now that we have these values, all we need to do is take our a, take our b, and take our c value and plug them back into our yp to get the first part of our particular solution. So our first particular solution is yp is equal to this equation. Now we have to solve for this portion right here. So for this particular solution, we have x e negative 4x. In this form, we use this f of x is equal to xk, a k being some number, times e mx. So in doing this, we have to first find our yp value, and since it is in this form, we have to use this yp. Yp is equal to a x times e negative 4x plus b e negative 4x. That's how it would normally be. This red right here, we have to multiply everything by an extra x, because up here in our last one, we had to do that as well to get it to be equivalent, so we can get our a, b, and c values. So after we do that, we take the derivative twice, and then after we take the derivative and simplify things, this is what we're left with each part. So the greens go together, the non-underlined part goes together, and the blue parts go together. So from here, we can start canceling things out. I noticed I made a mistake in my math. This 8 right here should actually be a 16, because if we multiply our 4 in, which is what we did for this, we distributed our 4 across here, we should be getting 16 bxe to the negative 4x. So once we do this, we can start canceling things out. We're going to cancel this part, and we're also going to look at this part to cancel. So we're going to look at similar values. We have this 16b and a 16b here. We have a 4b here and a 4b here. We have an 8a and an 8a, or negative 8a here. We have this 16 and this negative 16 here. So we are just left with this and this. And we need to set those equal to this, and we will find our a and b values. We can start to pair things. We can pair this x e to the negative 4x with this other x e to the negative 4x, and then pair this e to the negative 4x with this e to the negative 4x right here. And after we do that, we can cancel the x e to the negative 4x's and the x and the e negative 4x to find our a and b values. We found our a and b values, and using our a and b values, we can plug them back into this particular solution, add it to this particular solution, and add it to this general solution to get our final solution. For our complete y solution, we get this is our final solution. For number 13, we're asked to use variation of parameters to solve the following differential equations. First, we're going to look at A, and we need to solve the general solution, and then we need the particular solution. First thing that we're going to do is use this to find our y general solution. We have to use this yh and take the derivative of it twice. After we do that, we get this right here. We then need to use the quadratic equation to find our m1 and m2 values. Since they are complex numbers, we need to use this form, alpha minus I beta and alpha plus I beta. And we note here that our alphas are both 0 and our betas are 3. In the next step, we have to use this form to plug in our alpha and betas. After we plug in our alphas, we can see that this just becomes 1, and so does this. And after we plug in our betas, we see that in our cosine and sine, we have a 3x. So this will be our general solution. To find our y particular solution, we need to put it in this form. To get our u1 and u2, we need to use these formulas, and from here, find the values. To do this, we're going to look at our general solution. We are going to take our y1 value as being cosine of 3x and our y2 value as being sine of 3x. We can find the Wronskian using these two values. For our y prime, after we use our Wronskian, we're going to get this value, 3, as our w. Then we can go and use these equations and put them down here to solve for them. We solve our y1 prime and it looks like this after we plug everything in, and our y2 prime is going to look like this after we plug everything in. For y2 prime, we can cancel out the cosines because this tangent of 3t becomes sine over 3t cosine of 3t. That means that we're just going to be left with a sine of 3t on the top. And if we move everything out in here, since we know what tangent equals, we're going to get y1 prime is equal to negative sine squared of 3t over all of these x's should actually be t's. These should be t's as well since we're solving it in the form of t. So if we go back in here, this needs to be replaced and all of these values need to be replaced with t. We can just say that x is equal to t and replace the rest of these later. Finishing this up, we're going to have cosine of 3t times 3. Now we need to take the integral of both of these. Taking the integral of y2 prime is going to leave us with y2 is equal to negative cosine of 3t over 9. Now we need to solve for our y1 prime. We're going to put an integral in front of both sides. Use this sine property, and we can remember that sine squared of something, so 3t in this circumstance, plus cosine of 3t squared is equal to 1. From this, what we can do is move our cosine over, so it's going to be sine squared 3t is equal to 1 minus cosine squared of 3t. Since this is equivalent to this sine, we can plug this 1 minus cosine squared 3t in. We can move our negative 1 over 3 outside of the integral to make it easier since it is a constant. And then we're just going to divide our numerator, which is this now, by cosine of 3t. What that leaves us with is 1 over cosine 3t minus cosine 3t dt. Cosine of 3t, we need to flip it on the top, so that's going to be the equivalent of secant of 3t. From our instruction, secant of something, 3t in this case, is this. That's going to mean that u of 1 is equal to negative 1 over 3. And we're going to solve out the integral here. So we have ln, absolute value, secant of 3t plus tangent 3t in absolute values. And the negative cosine of 3t, the integral of that is just going to be negative sine 3t over 3. So in this area, there was a mistake. After we take this integral of secant, we still need to take the integral of the inside because of our chain rule. And once we do that, we can see that this integral is multiplied by 1 over 3. For the same reason why sine of 3t is over 3, because when you differentiate, it's the opposite of integration. So after you do that, that means all of this can be rewritten as over 3. Again, because of the same rule that we applied for the sine of 3t. We have to take the inside part as well as the outside part. Before we get our final answer though, to simplify things, instead of factoring this out, what we can do is actually separate everything, and then we're going to see that some things cancel out. Once we factor everything out, we're going to be left with this, and we can actually see that these values cancel out. And so we're going to be left with this as our official yp. So this is going to be our final answer. Y is equal to c1 cosine of 3t plus c2 sine of 3t minus ln secant 3t plus tangent of 3t in absolute values, divided by 9 times cosine of 3t. For part B, we're going to need to do the same thing. So first, we are going to find our general solution. To do that, we need to find YH. So we have our YH values. Now we just need to plug it back into our equation. So we are going to write something like m squared minus m. Actually, since there is no y prime, it's going to be minus 0m plus negative 1. From here, we can set this equal to 0 because this portion needs to equal 0. So this is what we're going to get for our m values. We can see this by multiplying these two. So we have m squared, we have m1, we have negative m1, so those are going to cancel out, which will get us this 0m, and then we have a negative 1, so it works out. That means our m values are going to be negative 1 and 1. We're going to have to make a note that our x values equals t because we have a t here instead of our x's, so all of these x's should be t's. That means when we use this formula, this is like the general formula. This is what you have to plug things into. When we use this, we are just going to have y is equal to c1 e negative 1 plus c2 e1. They're actually going to be t's, not negative 1. We have to include the t's up top. So this is going to be our general solution. Now we need to find the particular solution of this. To do this, we're going to do the same thing that we did last for A, where we have this formula. This is what we need. It's what we use. We're going to find our u1 prime and our u2 values, plug it into our Wronskian, and after we do that, since we have a prime here, we need to take the integral of that. So we're taking the integral of both sides. From our general solution, we can pull out our y1 and y2 values because we need those. So this is going to be our y1, and this is going to be our y2. Anything that's after the constant is a y1, y2. So we're going to have our Wronskian here. We're going to plug our y1 in and our y2 in. So we have these values. Right here is going to be y prime. So that's going to be negative t, and we have to have this as e to the t. And this is going to be w is equal to, we have to basically cross multiply and then subtract them. So we're going to have 1 because we're going to have e over e to the t divided by e negative t. So the e to the t just cancel out, leaving us a 1. And since we're subtracting and there's a negative in front of here, this is going to turn into a positive. And we're going to have the same thing where we have an e negative t. We have an e to the t over e to to the t, so that's going to be 1. So that means our Wronskian is just 2. Works out very nicely. From here, we're going to plug our values in. So we have our y2, which is e to the t, and our y1, which is e negative t. Plugging these in, we're going to get this. These are the values that we are going to get. From here, we are going to now integrate. So we're going to integrate this y1 prime and this y2 prime to get just y1 and y2. And to do this, we have to use integration by parts. From here, we need to assign our a and b values. So looking at this, we want our a to kind of deteriorate as it goes along, so it gets easier to solve. What this means is we're going to set a is equal to t plus 3. When we take the prime of this, it's just going to be 1, because this 3 is a constant, so it's 0, and t just becomes 1, so we're just going to have dt. And our db is going to be, there's actually going to be a dt on the ends of these. So our dt is going to be, for the first one, it's going to be e to the t dt. E t dt. And if we integrate that, we're just going to get et dt, because that doesn't change. Now we have to plug these values into here. This is what we're going to get. Taking the integral of this side, we're just going to get et. And if we factor this et in, we can see that we have tet plus 3et. And we can simplify this to be tet plus 2et. Now we have to plug this back into this, because we still have a negative and a 2. From here, we can move the constants out of the integral. So we're going to have negative half. And our integral was just et t plus 3. So we're going to have to plug this in. This is what we get. And now we need to solve for u prime of 2, which isn't much different. We're still going to use this format. The only difference is that we have an e to the negative t. For this second, by parts, we have to note that the only difference is we have a negative e, or an e to the negative t. So this is how we're going to write it. And then when we integrate that, we are just going to get a negative e negative t, because this integral has to come down. And then if we take the derivative of this part, we bring this negative down again, so that makes it a positive e negative t, which yields this. So plugging everything in, we're going to have t plus 3 times negative e negative t. And that's going to be subtracted from the integral negative e negative t dt. These are both going to be positive. We can factor this e to the negative t in, so we're going to have negative e negative t minus 3e negative t plus, when we take the integral of this, the negative comes down, so it's going to be negative e to the negative t, like that. So it's going to be plus a negative e to the negative t. From here, we can add these. This is going to stay the same, so we have negative e to the negative t. Add these two, so we're going to have negative 4 e to the negative t, like this. So that means this is our y2 value. We're going to plug it in to here. Notice that we have this 2 as a constant. So that means we have a 2 out front, and in parentheses, we are going to have the equation that we found. These are our y1 and y2 values. We just have to plug it into this formula right here to get our y particular. We're going to have u1 times y1. We can write our y1 first, and that's going to be e negative t. And then in parentheses, we are just going to have our u1. And this is our u1 right here. And we see that we have to add our u2 and y2. So looking at our y2 first, we can see it's et. So we're going to have et out here. And we can copy this part and put it in like this. So this is our yp value. we can simplify, and that's what we should do. So we're going to distribute this e to the negative t and this negative 1/2 into here, and same thing for this other side with their values. We did forget that this e to the negative t has a t in front of it, behind it. So we make sure to include that e to the t. I lost that. So this should be negative t times e to raised to the negative t. That means we're going to be left with a t in here. So we're going to have a t right here. And that means when we combine all of this, we are going to have a negative t minus 3. So this is going to be our y particular. All of this work will turn into this for our y particular. We can factor out a negative 1, so we're left with yp is equal to negative t plus 3 to keep it looking nice. And now we need to combine this with our general solution, which is this one. That means our final answer is just going to be this. This is our solution. For number 14, we're asked to solve the following differential equation. To do this, we use the Cauchy-Euler equation, and we need to have it in the form that looks like this. So if we have an x squared, we need a y cubed, and if we have in this case, it's a 0x first y prime. If we have an x to the first, we need a y prime, first derivative. If it's x squared, we need second derivative. And if it's x to the 0th, there is no derivative on the y. Same thing for b. We have x squared, so we need y to the second derivative. We have x to the first, so we need y to the first derivative. And here we just have a constant. Part A, we're going to follow a series of steps. The first step is that we use y is equal to mx. We're going to plug this in for our y. But we need to take the derivative and antiderivative so that we can plug it into we need to take the derivative twice so that we can plug it into our equation. After we take the derivative once, we're going to get, actually this should be xm like this. We're going to get m and x, m minus 1, and then we take the derivative again. So this is the second derivative. We're going to get m times m minus 1 times x m minus 2, actually. xm minus 2. So we have this now, and we need to plug in our values. We have these, so we have x squared times our y double prime value. And if we plug this in, we're going to see that we have our x squared. And it's a good time to really break up these y's. So instead of writing x m minus 1, we can write x to the m times x negative 2. And then next we have minus 30y. So minus 30xm is equal to 0. Now that we have this, we can cancel out our xm's. We're really dividing everything by xm, and since the right side is 0, it is still 0. And these x2 and this x negative 2 cancels out, so we're just going to be left with m squared minus m minus 30 is equal to 0. In finding our m's, we're going to see that we get m negative 6 and m positive 5. So m minus 6 and m plus 5. From here, we can set our m values to be 6 and negative 5. We're going to then plug this back into our y value right here, just like we have done before, except this time we have only one m here and we have two m's here. So that means this needs to be rewritten as y is equal, since this is general solution, we're going to find y is equal to c1 x 6 plus c2 x, and we have a negative 5. And the equation that we're plugging it into is just y is equal to c1 xm plus c2 xm. That's what we're going to use. That is our answer for part A. For part B, we're going to do the same thing since it's in the Cauchy-Euler form, and we are going to use this. So we're going to do the same thing, just with different numbers. From here, we're going to plug in our values. We have our x squared, same kind of as last time, m minus 1, xm, x negative 2, again because we separate our xm minus 2. And then we are going to subtract a 5x. We have a y prime here, so we need to plug in y prime being m times xm times x negative 1 plus 9 is equal to 0. And then after doing that, we can cross these out. We can do the same with this x. So this is actually written incorrectly. There should be a y here, because if we have a constant is actually not allowed. We are going to also have a y right here. And since we have that, this x of m needs to go right here. So since our x of m is here, and we have an x of m here and an x of m here, we can cancel them out. Rewriting this, we're left with m squared minus m minus 5m plus 9 is equal to 0. We're going to have m squared minus 6m plus 9 is equal to 0. From here, we're going to have m minus 3 squared. So that means our first value of m is equal to 3. Since we have repeated roots, we have our first m1, but we need to get reduction of order. So we need reduction of order, and this means that we need to plug this in to our equation, which was this. We need to plug our results into this. So once we have this, we can see that our first value is going to be y is equal to c1 x to the 3 plus c2 x. We don't know our m over here yet, so we just have to solve that again with reduction of order. This is our reduction of order formula. We have our y1, which is x cubed, so we're going to plug that into here. We remember that our p is whatever value is in front of y prime. So since there's an x squared here, we have to divide everything by x squared. So after this cancels out, we're just left with the 1 y double prime, and this is going to be x. This is going to be negative 5 over x. So that means our p is going to be negative 5 over x. And you take the integral of p of x, and just putting p in, we have negative 5 over x dx. We can see that these negatives are going to become a positive. This 5 is going to be moved outside of the integral, and this integral, we can rewrite this as the integral of 1 over x, of 5 1 over x. And the integral of 1 over x is just L of n. So again, rewriting this, we have e 5 L of n x. This 5 can be moved inside of the L of n, so it's going to be ln x to the 5th, and that allows us to cancel out our e and ln. So that means that we are just going to be left with an x to the 5th. I can draw an arrow and go over here and rewrite everything, as we still want to make sure we have our y2 equals over here, so we remember what it's solving for. We have our x cubed out front, and we have a e, or actually our e is gone, so we have x to the 5th over x to the 6th d of x. This is just going to cancel. Well, it's going to subtract, so we're just left with an 1 over x in our integral here. And if we keep going, we're going to see that we have y2 is equal to x cubed, and the integral of 1 over x is just ln of x. If we wanted to include the constants, technically, when we take the integral of this part, we're given a constant. So we have to have a plus c in here. But e to the c value is just c, and that c is moved out front here. So we're just going to have c is out front with our x cubed. And then when we take the integral of this inner part, we're going to have another c. So we have plus c2. And this will be in parentheses because we have this c1 out here. So since our c1 is this up here, and it is equivalent to our c2 right here, we can basically just take what we got here and write it as our y value, because this has to include both of the parts that we found. And that is the answer for 14b. For number 15, we're given a couple of questions to answer, and it's asking us, do y1, y2, and y3, all of them being constants, form a fundamental set of solutions for the differential equation y prime is equal to 0. We need our solutions, our set of solutions, to be linearly independent. What that means is that the Wronskian of these cannot be 0. It needs to be linearly independent. The easiest way is to check with a Wronskian. So basically, if we plug all these into a Wronskian and we figure out how all of these values work, we can see if it's linearly independent or dependent. And an easy way to see this, especially for constants, is if we do this. So we need our, we're not going to solve it all the way. We actually don't need to. We have our y1, our y2, and our y3. Looks like this, right? So when you take the derivative of a constant, it's going to be 0. If we look back at 7, we can see that all of these, all of the parts that are in parentheses, they're all derivatives of something. So that means in the end, it's just going to be 0, 0, and 0 all added together. And if it's all zeros added together, that means it's going to be linearly dependent. But we need this to be linearly independent to form a fundamental set of solutions to this differential equation. So that means this does not form a fundamental set of solutions for the differential equation. And that's how we would write it. We would just show this, and we would really, it's better to write out the Wronskian. So basically write out this part, plug all these values in, plug all these values in, and show that they equal 0. And that would be a great way to show, kind of prove why this does not form a fundamental set of solutions. Now, the next question is asking if a sine of 5x and sine of negative 5x are linearly independent. We could do the same thing. We could plug it into our Wronskian. So after we write out our Wronskian, plugging in our y1 and y2 values, this is what we're going to get. Now we have to cross multiply and then subtract the products. We have this one multiplying with this and this multiplying with this. What's going to end up happening is that we are going to have a sine of 5x times a negative 5 sine negative 5x minus 5 sine 5x times sine negative 5x. Since these are exactly the same, they're just going to add to be negative 10 sine 5x sine negative 5x. And since we can plug in zeros here for our x's, we got to test these, we can plug in a 0 here and a 0 here. That means this is going to equal 0. It can equal 0, which means our Wronskian is linearly dependent because our w can equal 0 So when it asks if y1 and y2 are linearly independent, well, we need to remember that if it equals 0, it is linearly dependent. This equals 0, so it does not equal 0, which means it is not linearly independent. And that is the proof for why B is not linearly independent. For C, we're asked to suppose y1 and y2 are solutions to a differential equation. Is it possible for the Wronskian w y1, y2 to equal 0? Yes, it is possible, because it is one of the key parts of the Wronskian. It can only equal 0, or it can equal not 0. So it either equals 0 or it does not equal 0. So when it asks, can it equal 0? That means yes, it can equal 0. There is a possibility that for some y and for some y1 and for some y2 value, it does equal 0. So yes to this, but the solution will be linearly dependent and it cannot be linearly independent. For part D, we're asked to suppose that y1 and y2 form a fundamental set of solutions to a differential equation. Is it possible for the Wronskian to equal 0? So if they form a fundamental set of solutions to a differential equation, recall that they have to be linearly independent. And for something to be linearly independent, it cannot equal 0. So going back, if it does not equal 0, it is linearly independent. And we need it to be linearly independent for it to be a fundamental set of solutions to a differential equation. So we mark that it cannot equal 0, and we check back here. It asks, can the Wronskian equal 0? That means no, it cannot equal 0, because if it's linearly independent, which it needs to be to form a fundamental set of solutions to a differential equation, it cannot equal 0. And that is it for 15. And that is that for the study guide.